There's probably about 4 or 5 people gone today. So I'm going to go ahead and just write these answers down. If you have it done, check them. If you don't have it done, then you can at least write them out, the answers. And then if you want to work through any, we can. Okay? Probably just one's all we need to work through, because I think for the most part, students have done a really nice job. Asked very few questions on these. So the answer for 238 is 4.2 liters.
Hey, Aaron, who's right?
Okay, the answer for 240 is 60.3 milliliters.
Oh, it's 60.2.
243
3.0.
is 3.01. I don't know, that's what's in the book.
You take 2.75 times 318 and divide it by 291.
Yeah, that's not those numbers.
247
Wow. 115.3 kp.
is 115 kPa.
I did the first problems right.
420.
I got 118.
259
Oh, I was off on that. Oh, 420.
is 233 Kelvin.
Oh, I was off.
And 261 is 0.899 atmosphere.
I just rounded.
Okay, we can take a look at a couple that you want to real quick. They're pretty easy setups. Any of those that you want to take. Now, if you're off by just a little bit, like significant digits, don't ask. Because you're doing it right. It's just based upon numbers that you're putting down in your final answer. Okay, Tabby?
261.
Okay, 261. 261, when we look at it, we want to read through it first to see what we're given. So, we'll read through it before we write anything down. It says you got a 2-liter bottle, and it's containing air that's sealed, and the temperature is 22 degrees Celsius with a pressure of 0.982 atmospheres. That same bottle is placed in a freezer and allowed to cool to a minus 3 degrees Celsius. What is the pressure in the bottle? So we're finding P2, right? Some of you get confused when you're given numbers you don't use because the 2-liter bottle doesn't change in its volume. 2 liters, 2 liters is the same when it's outside the freezer than when you put it in the freezer. Still 2 liters. Okay? So volume is not what we're going to look at. It is a variable that is unchanging. It doesn't change. So what we're looking at is pressure and temperature. So on that one, 261, it's P1 over T1 equals P2 over T2.
Yeah, I did the wrong equation.
That's okay. All right. Does anybody want me to go further with that?
Yes.
Okay. So, cross multiply. I like cross multiplying. Gets rid of variables that you need to solve for sometimes. That's in a denominator. I just do it with symbols. A lot better to do it with symbols than numbers. Okay. So then it becomes P1 times T2 equals P2 times T1. Right? Then at this point I need to know what I'm all given on that one. So the temperature is 22 degrees Celsius. So we'll list them out here. P1, T1, P2, T2. Okay? So 22 degrees Celsius transfers into Kelvin. So it would be 295 Kelvin.
Oh, I forgot.
And the pressure is 0.982. New temperature is -3, which is 270 Kelvin. Try to just put Kelvin in there, because some of you, I know what you're going to do. You're going to put 22 degrees Celsius in for T1, and you're going to put -3 in for T2, and you're going to leave those and forget to convert them.
Yep.
So convert them right away. Don't even put Celsius in your setup. And that way, you won't have to worry about it. Yes, Harley?
Okay, so I did exactly the same thing, but my answer, I got .982.
Yeah, I don't know. It might be how you calculated it the first time. Maybe you pushed the wrong button, or maybe you didn't go as far as you needed to. I don't know. But that's probably the right setup. So then, what we do is just substitute in our P1 is 0.982. And then our T2 is 270. A lot of times students mess up on the temperature because they'll put in a T1 up here. Because they won't take their time and go, oh, it's the second temperature. So 270 Kelvin, and then that's divided by the 295 Kelvin. And then you got your answer, which is 0.899. Okay? That's what the book has. I didn't calculate it. Is that what you guys have?
Yeah, I got that.
Okay.
I don't know. Flip your 295 and 270. None of it's pressure 1 and temperature 2.
Any others?
And that's temperature 1. That's temperature 2.
259.
I did the same.
259?
Yeah.
Okay, real quick,
What?
we'll do 259. 259, it tells us we have an elastic balloon with a volume of 6.75 decimeters cubed at a temperature of 40 degrees Celsius. What's the temperature at the volume of 5.03 decimeters cubed? So basically what you do, it's a V1 over T1. So it's V1 over T1 equals V2 over T2. So then cross multiply V1 times T2 equals V2 times T1. All right? We are solving for what's the new temperature? T2. So then it becomes V2 times T1 over V1. Nope. V1. So then when I have my numbers here, it's V1, T1, V2, T2. And I plug all my numbers in. So it would be 6.75 and 313. Okay, and then V2 is 5.03. And then we're solving for T. And when you plug them in, it would be 5.03 times 313 divided by 6.75. And then you'd get an answer of 233. Okay? Okay. The new concept today is just same, just more variables, same type of setups. Couple more variables, same type of setup that we're going to do. So, you don't have to write this top part in your notes when you look at it, but we're going to look at what's called, we're going to combine all those, we're going to combine all these laws into one law. So we're going to incorporate pressure, volume, temperature, all in one law. So it's called the combined gas law. Okay? So the combined gas law looks like this. It's P1 times V1 over T1 equals P2 times V2 over T2. Okay? Now this is a situation where you don't have control over some of the variables. Like when we did Boyle's Law with the syringe, our temperature in the room remained the same. So temperature remains constant. When we did Gay-Lussac's Law with the flask, kind of like that one problem, take the 2 liter, put it in the freezer. We took that flask with a set volume and placed it in different temperatures of liquid. So it did not change the volume. Sometimes an experiment that you do, you'll have multiple variables changing. So if that's the case, then you can just combine it all into one law. Right? Now, this is the one all you need to know to do all 3 of these problems plus the combined gas law. Because here's what you usually have happen. It'll tell you what remains constant. So they'll say, all right, this is the pressure and volume initial. Here's the final volume. What's the initial pressure keeping temperature constant? Guess what? We take temperature out. What are we left with? Boyle's Law. If it says pressure remains constant in the experiment, doesn't change, then we have Charles' Law. Okay? Cover up the P's there. If volume remains constant like the flask we changed, then we get rid of V1 and V2 because they're the same numbers. They're going to cancel out anyway. Why plug in those numbers if they cancel out one another? So you can use this law because all 3 of the laws above are combined in one setup. So I'm gonna do one with you, okay, and then we'll do the calculation, and then I've got a couple for you to do for tomorrow, just 2. All right. So you guys probably have your book out. We're gonna look at problem 249. 249 on page 896. 249, page 896.
Science these days.
Yeah, mine don't take it.
Yep, if you had everything written out, even if you maybe didn't have the last problem all the way done or whatever,
What's my 96?
896.
That's what I meant to say. 896.
You're only off by 600.
Okay, that's enough.
You're close.
I've heard enough from you today. No English self-teaching.
Not that close. Okay.
You guys are on the recording. Did you guys know that?
Yeah.
Okay.
We actually?
Yep.
Shout out to Cam Jurgens. Cam
Right
Jurgens,
now.
president.
Okay. We're going to take a look at this setup. You've got 6 variables that you have to keep track of. So, do a good job, just like we did before, writing things out. Most of you were writing things out the proper way because there's lots of variables. You miss one placement of those, then the answer's wrong. Okay? And I know you do make mistakes. I knew I can look and give you kind of seeing what you're doing. You make a simple mistake, but if you don't write anything out, I can't really see where you're making mistakes. I don't know if you're doing it right or not. So we know the next one we're going to do is the combined gas law. So we know what that would look like. What I want to do is I want to get rid of any variables that's dividing. And so I cross multiply right away. And that's going to be my starting point. So I'm going to cross multiply, and then that ends up to be P1, V1. If you notice, T, when you do the temperature, it's always opposite of the pressure and volume. Okay? So that's going to equal your P2, V2, T1. Alright, so I'm ready to go. I know I'm using the combined gas law. We'll look at all these variables, V1, P1, T1, P2, P2, T2. Okay, the volume is 450. The pressure is 100 kPa. The temperature 17 degrees Celsius at 273, 290 Kelvin. Volume. It wants to know the volume. Pressure. It's at 101.3. The temperature is at 0 degrees Celsius. So that would be 273. Okay? So then, at this point, I know V2 has to be isolated. So then, I'm going to divide both sides by P2 and T1. So then my final setup to solve for V2 is P1, V1, T2, divided by P2 and T1. And that gives me V2, any volume. So I just plug my numbers in. 100. Volume, 450. This is where students make the mistake. They're not, so they'll put 290 in. But it's T2, has to be 273. So if you catch yourself, hopefully you won't make that mistake. And then P2, 101.3. And T1 is 290. Then you got your answer. Yes, Tabby?
We don't have to change the KPA to...
You do not. You do not. You can leave it. Because what happens, Tabby, is Kelvin cancels, KPA cancels, and my only unit left over is milliliters. And that's what I want to find, volume in milliliters. Okay? So then the answer for that one is 418. Okay, it'll be 418. So the problems that you'll need to do, add on to those in your notes, would be 248C, as in cat. Unless it starts with a K and then stops. Okay, 248C. And 273. We like 273, right? 273.
What, on the same page?
Yeah, you can put it on the same page. 248C. And 273.